All right. How are we doing? We got time left? Or are we done? Time, more or less. What? 10 minutes. It's amazing how how much material we cover. How's everybody doing so far? You guys back there okay? Good. I like you. You tell me okay sometimes, okay? All right, well, we got 10 minutes. All right, so now I guess we're moving over to, positions and binary trees and stuff, right? So, so we're going to have this is going to be a linked binary tree, right? It's a class. And we're just defining this object when some user wants to use our object, right? They call this, what does this do? What does this code actually do? It sounds like what you want it to do, but it's not. What does it actually do? Right? It creates a location for something that is able to point at a binary tree, right? But the binary tree is not actually created, right? Good, right? That's kind of why, I'm sort of good. We're doing this, right? Right? Tree is going to point at the new object, right? It's a type. Right. So if we want a new one, then this routine is the constructor, right? You don't have to declare it. They're saying it's a default constructor. You call it, it constructs whatever a binary tree is, and tree now will point at it, right? So maybe the moral of this is you should never have this code, right? Why would you ever want something that's not pointing at something, right? Maybe you should always do this. All right, so there's tree. Somehow we constructed this thing, it's pointing at that, right? Right, and so, and what does it construct? Does it construct this? No, it probably constructs sort of the empty tree, right? So this is some book. So when I first taught this course, it's the first time I learned about object-oriented programming, right? When I went to school in '82, before your parents were born, maybe not. I was exaggerating. Every story needs a little exaggeration, right? All right, so when I went to school, they were all excited, just like they were excited a few years ago about object-oriented. When I went to school, they were excited about a new paradigm, which was Fortran, right? It was structured, right? Before that, just before I came, they were doing gotos, spaghetti code, right? You know about that? You can write code that pops all over your code, and why is that bad? Is because it was impossible to debug, right? And so then they put in these rules. Well, you need to have routines, and you need to have loops, and you need to have ifs, right? That's what they were doing in the 70s and the 80s, right? And then at some point, I don't know when object-oriented started. I started here in '95. They brought in Java about then. So let's say '95, they started doing object-oriented. All right, so anyway, why did I get onto that? So here, when I started teaching here, and learning about objects, I had to go to my friend Frank, who was a professor and is now associate dean, and say, I don't quite get this because I think about, there's a difference in my world, I point at the root of the tree, then I have the tree, right? But tree is not pointing at the root. It's pointing at this big box, right? Which has root as a field. So they're slightly different, nuanced things. And when we get into recursion, that difference is going to be a problem. All right? So let's understand what this is. Tree is of type pointer to this tree, or is a tree, and it contains two fields. It contains root and size. So do we get here, right? Well, first we define what a node is, right? A node. This is a type node. It's kind of inside of tree. So only the tree knows about node, right? Remember about hiding? We're hiding nodes, so the outside world doesn't know what your nodes look like. And what do my nodes have? They contain an actual value, a pointer to the parent, the left child, and the right child, right? That's what this box is. It doesn't show the value, I guess, right? And then it doesn't allocate memory, right? And then this tree also contains a field which is the root, and initially the root is pointing at nothing. That's this guy, and right, and then we're going to make root private. So again, nobody in the outside world can touch your root, right? If you want to play with my tree, you have to do it. We have to be more familiar, right? You have to go from, use my routines, right? So then, right, it's private. And then the outside world, let's think about the outside world. It wants to be able to point at objects in your tree, right? But can the outside world point at a node in your tree? No, because the outside world doesn't know about your nodes, right? It doesn't know about your nodes. And this is where, I start rolling my eyes a bit, right? So we want the outside world to point at these nodes, but, so maybe we do make the nodes public. We could make the nodes public, or you can do these weird tricks, right? So, right? So maybe it doesn't need access to left and right, right? So we could make it private, right? Now PI is not a node, right? It's a pointer to a node. And so we're going to abstract it as a position, right? And so here we're going to say node implements position, right? So position is an abstract data type which allows you to point at things, right? And you can have many implementations of it. And one implementation of a position is a pointer to a node, right? A pointer to a node is a position, right? So my node, that's where it gets confusing again, right? Is node actually a node? No, it's a pointer to a node, right? Why? Because that's why it can be a position, because a position is not a node. A position is a pointer to a node, right? Why I hate Java. All right, so here, right, node is going to be a pointer to a node, which is in fact a position. Now we're running out of time? Good, because we're getting muddled with this anyway. Let's all breathe until next class, and we'll figure out all these things, right? I hope that was not too easy and not too hard. When I refer to a textbook once in a while. So I suppose you could find that one. I don't know if, I don't think Jackie uses one. Certainly, I'm never going to assume you know anything that's not in the slides. But if you're not, you need more extra things, I suppose you'd get it from. These days, I Google stuff and look at ChatGPT and stuff. All right. So this is what we were doing last class. We were so we're building a structure out of pointers, and this structure is this binary tree, and we had that each node has stores some data for that node, and then it points to a left child or right child and a parent, and you'll see. I remember I've told you the empty tree is a perfectly good tree, which allows you that every node has a left child and a right child, and one of those children might be the empty tree. So you can see the little nulls, those little circles with the arrow, the line through it. That's another symbol for sort of the null symbol. It's pointing to the empty tree, and then you can see the data is this various cities, and so the class for these linked binary trees, it contains the description of the nodes, so nobody outside the world knows what these nodes look like, and then you have on the outside world, it wants to be talking about particular nodes in the tree as this abstract concept of position. But the outside world can't know about nodes. Now, right? So I'm quite frankly, have never experienced enough not to think that this is a little silly, but maybe it's useful. We're supposed to cover it, so I guess it must be a little silly, right? So you could make the node public to the world, but you're supposed to hide it. So instead, you make it private, and then the outside world can't talk about a node because it doesn't know it, right? So it thinks about it as a position, right? And so here we're going to have there's going to be this class of position, and the node is going to be an example of it. I mean, there could be many positions. Where your finger in a pie is could be a position, and one of these nodes could be a position. And so I was pointing out that one of the sort of contradictions between this concept that the variable node, is it of type node? Is it a node or is it a pointer to a node, right? I push that it's a pointer to the node. Why? Because it's a position. I don't know, or maybe you could say the node is a position. I mean, I guess that's fine too. So anyway, what are we going to do then? Then we're going to say the outside world has all these various positions within the tree, which are, I guess, are nodes, but it doesn't know they're nodes, right? And then what are the various things the outside world can do? It can say, I have a tree, and there are many routines that I can call, and one of the routines I could call is root. They're not called routines, are they? They're called methods, right? So the tree has a method called root, and what does it do? It returns a position, right? It returns the root position, right? So now P1 is pointing at or is the root, right? Now, so that's called, the root is called the method within the tree. It's public because the outside world needs to be able to know about it. And it returns something of type position, right? So, right? So, but root is, right, it's a private variable that, you can see it up there in blue. It's a private variable, and it's of type node, right? So if you're supposed to be, I remember the problem is, right there it is. So, oh yeah, so here, see, it's returning a position, even though root is of type node. But, you can, I have these great markers here, right? So if x is a real number and I is an integer, and you do this, then it takes this, it might get upset if you do that one. Why don't we do it this way instead, right? You can take the integer and store it as if it's the real number. This way, it's got to figure out how to round it, right? So that's kind of what we're doing here. We're taking, it's probably like the is a thing, right? An integer is a real number, but a real number isn't an integer, right? So here, what do we got? We got here is the root is a node. A node is a position, so you can return it like that. All right, so what are some other routines? This routine is you have a position already, and you want to say, give me the right child of that position. That's sort of the walking down the tree. And so here we can have this code where you pass it at P, which is a position, and then you go from P to P dot right and return the position in the right? Now, does this code look good to you in terms of this whole position thing? You type it in, you think it's good, and it's just, everything's filled with bugs, right? And so, it's taking position as input. Now, of course, when you call it here, you're calling it with P1. So the value in P1 gets copied into this local variable P, right? And P is of type position. So can I say P dot right? You'd like to, but I don't think you can, right? Let's. All right, so here we're kind of saying you can, right? P dot right is there. What is it pointing at? It's pointing at this guy here, right? So P2 is now pointing there. I mean, that's certainly what you want it to do. Everybody kind of follow that? Here's the oops that it's funny. The truth, you want me to tell you a secret? I don't look at these slides. I made them 5 years ago, but I sort of remember them. So here's sort of the oops. The oops is that P is of type position, and position doesn't have a right field, right? So you have to do something to cast it, right? And so what we're going to do instead is the value P1, which is pointing to the root node, is a position. So it gets copied into P, which is a position. So we bring it into the routine. Now, the problem with P in the routine is it's a type position, so you can't say dot right. So then you have to make a new variable, which is a node, right? And so I guess it's like when we do this, if x is 3.8, then maybe this crashes. But if x happens to be 3, it happens to be an integer, then it copies over, right, in real time. So in real time, P is a position, which could be a finger in a pie, right? But if it happens to be a node, then we can copy it over to N, right? Now, N is a node, so we can do N dot write and return that value, right? And again, there's a casting because N dot write is of type node, and so when it gets returned, right, into our code, returned to our outside world, it has to turn into a position again. All right, so you can, the two things that we're learning here, what I really care about, right, is the linked list, is the tree structure and how we move around it, and on top of it, we're learning this abstract data type, right, of positions. And I was told to teach it years ago. Yes? I think, I don't know. It's in the book that I was reading at the time, and it said how it would declare it, and I don't know whether Java knows about it. It could be that you have to bring in some library. I actually don't know. How about look it up? Yeah.
Like the beginning of the binary tree. So let's say like Chicago and New York.
I think we're going to get there, but you would get if you wanted to get to Chicago, you would start at the root and then you'd go left, and now you have some variable pointing at that right node, and then you would say, give me your data, give me your element field, right? So if, yeah, if the last homework assignment I did 5 years ago was moving around these trees with these positions, and it's probably what we would have done if Jackie hadn't come and said he was going to do it all for us. All right, so here's another routine, which is saying I'm at some tree stored by P2, and I want to get the sibling, right? And so I'm here, and what do I want to do is move over there, right? And the code is a little trickier than before, right? So, right, because if I'm on the right, then I want to return the left, right? And if I'm in the left, I want to return the right. You know what I'm saying? If I am my parents' left child, right? So look at our code here. So you'll see I put in little fonts that P has to be translated over to N, right? I didn't make it big because it stops fitting on the page and because it's sort of silly anyway. All right. So now we have P2 in N, and now we have N pointing at more internally pointing in. You can kind of think about it as P2 outside pointing at this position and N more locally pointing at the same node, right? So now we have N is here. And what we have to find out is, am I my parents' right child or left child, right? So we can say N dot parent is my parent, right? So here, right, I'm here. This guy here is, do we go through it? Maybe we even, no, we don't go through it. All right, so I'm here. This is N. n dot parent is up here, right? N dot parent right is here, right? And is that me? Yes, it is. It is me. So who am I going to return? I'm going to return n dot parent dot left, right? And if it's not me, I'm going to return, that means I'm over here. So I return n dot parent dot right. Right? Does that make sense? Now, when might this crash? Hmm? Yeah, when you hit a null in there. Well, actually, if I'm here and this is a null, that's not a problem because I return my sibling could be null. So that's not a crash. Yeah. Yeah, that's kind of what he's saying. Suppose it's I don't know, we don't have an example here. But if this stuff wasn't there, then I would be returning null, and that's not a bug. The bug is suppose n's the root, then you can go to n dot parent is null, and then when you say n dot parent left, that's when it crashes, right? So you probably should check in here to make sure you're not the root, right? Oh, and in fact, there we did it. See, it's amazing how somehow my slides know, right? So there it says, you better not be the root, right? Everybody following this? All right. And then, in case you want to find out where where Seattle is, right? P2 is pointing at this guy. So can we have this code here? P2 dot Seattle element and get Seattle out of it? No, you can't. It's that typing stuff again, right? So in C we would just do this kind of stuff, right? But we're not allowed to. So we have to say tree dot get element, right? And then it says I'm going to give you a position P2. What are we going to do? We're going to cast P2 to being an N, and then we're going to return N dot element, which is of type E, whatever E happens to be. Right? Are everybody kind of following this? Yeah. 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 All right. So what an exception in general means? This exception. All right. So suppose I pass this routine the root, right? So this is what I'm checking. If n dot parent is null, right? So if I'm pointing at the root, if I'm the root and I say dot parent, then who I'm going to get is null. And then when I say, so n dot parent is null, and then when I do dot right, we're going from null, who's the right of null? And null is not, there's nothing there, right? So it's going to crash at this, if n dot parent is null, then it would crash right here. And it crashes by, I don't know, they throw exceptions and things, right? Does that make sense? In fact, I guess anytime you follow a link, you got to check to make sure there's something there, right? Are we saying anything new here? This is position. All right, so I guess this routine, I guess the point of this slide is that you don't necessarily have to write it separately because at least it's talked about in position knows that it's going to have something of type element, right? You might have to implement it in here, right? Here. So here, position talks that it should have a routine get element, but doesn't implement it. And so here, when node implements position, then node should write the get element routine, right? Should call it get element to line up with what we already have, right? Does that make sense? And in some ways, I think my slides here are kind of unfortunate because I'm teaching you two things at once, right? Well, maybe three things at once. We're doing a little more pointers, we're doing a little bit more of trees, and we're doing this kind of inheritance of nodes and positions. So it's a little busy, right? Are people good? All right. So now we're going to Toronto, of course. We say, hey, this is kind of American, and we want to add Toronto, right? So here we're going to say P2 is pointing to someone, and P2, I happen to observe that P2 doesn't have a right child, right? So we're gonna add a new right child to P2, and we're gonna call it Toronto. Right? Everybody see what we're doing? So that's what we're doing. We're sticking it in there, and we're calling it Toronto. And then what we're doing is we're returning the pointer, the position of the new node, and we're storing it in P3. Right? So what do? We're given a position, and we immediately put it over to our node in, right? And then we have to create our new guy, right? So we can say, hey, we want a new node. And when we design our routine node, we can have a constructor with as many operands, inputs as you want. And since there are 4 fields, we might as well have our constructor just put them all in. All right. So it's written up there. Who do we want our left to be? No. Who do we want our right to be? No. Who do we want our element to be? Toronto. Who do we want our parent to be? N. Right? Everybody follow that? So there, Toronto, where are we tracing all this, right? Toronto gets, here I'm kind of tracing it, right? We want Toronto here, so we pass Toronto in, so Toronto goes in by E, right? So we put an E there, right? And then who's our parent? Our parent is this guy. Who is holding this guy? N is, right? N knows where that guy is. So, but where did N come from? N came from P2, right? So there's P2, we're passing in the P2. That's where this value comes from. So there's P, and then it goes to N, so we can plug in there, right? There's lots, see, there are an awful lot of places where people are referring to that. Did everybody kind of follow that? And then what are those doing? Those are both nulls, right? And and then we have to get this pointer. How do we get to that spot there? Right? Who's holding this record? Right? Node. Who's holding this node? N is, right? And then n dot right, right? Is that little box up there? And so then how do we get, right? So what does this thing do? New dot node creates a new node and returns the pointer to it, right? So we want to put it in that box. So what do we say? We want to, right? This is what we're doing. We just do that. Right? Everybody follow that? I mean, there's a lot in this line of code. Yeah. All right. And so P3 then gets the value and is pointing at it, right? And all right, so now what value do we return? Right? Here we want P3 to get a value. Well, it's the value returned. What value do we return? And what do we write down in the question mark? Right? N dot right. Right? That's who has it. Right? Everybody good? Right? And right? And we can put in some extra conditions. Here we're checking to see that n dot right is empty so we don't drop anybody. And if it does have somebody, then you can decide what to do about it, right? You could drop him if you wanted to. You could, here what we're saying is he already has a right child, right? We're throwing an exception. How are you guys doing? Everybody good? Excellent, right? Oh, here's another thing. We also have, all right, so we're going to learn in the next set of slides about system invariance, right? And a system invariant is some properties that are supposed to always hold. And one of the properties that we can make up here is that the variable size is supposed to tell you how many nodes there are. And we just change that, right? So we want to stick in here an extra little line here that size equals size plus 1. Right? All right, so how would we build this tree? Right? Well, we would get a tree, right? We have a new variable outside the right. Now we're outside the world, right? We're a user on the outside. And what do we know? We know that there's these things called linked list binary trees. And this says that our variable tree is going to be of type pointer to a linked list binary tree. But that doesn't allocate the memory for it, right? So we get a new one constructed, and tree is now going to point at it, right? Tree is one of these things. Everybody good? All right, so then we say, oh, I guess we have we can't say, we wrote a program, add on the right, but that's not going to construct the root for us, right? We need a new routine that says, give us a new root. So this says, give me a new root and have it be Providence, right? And return it to, store a pointer to it into P1, right? Now we have the root. And then, right, then we could say root's left child is Chicago, and P2's left child is Baltimore, and P2's right child is New York, and P1's right child is Seattle, and P3's right child is and P2's right child is Toronto, right? You might say, why did I was trying to mimic the tree in my indenting, right? Everybody kind of good with that? All right, so any questions? Everybody good? Yeah.
The constructor, doesn't it create the root as an attribute? Because he added an extra line, add root.
The constructor for the tree?
When we call the constructor of the tree with the new keyword, what does it construct if it doesn't construct the root and the side?
I'm pretty sure. I mean, if you don't write, I don't think we wrote anything to do anything. And if you don't write anything to do anything, all it gives you is the box with the variable root and with the value 0 and the variable size with value 0.
Oh, okay, so when it created it, the root was null, and then when we add the providence.
Yeah. Yeah. So it started with root being null. And so then we would have to write a routine that changes the value of root from null to being something, right? And I can imagine saying, I'm in a world where no tree should be empty. So you could write a constructor that not only does it construct the thing, but it insists that it creates the first root if you wanted to, right? All right, so, okay, now we have 2 trees, right? Here we're making very Canadian thing, right? Maybe we'll be the 51st state, right? That was a joke. Right, so now what we might want to do is we want to merge these somehow, right? So what we want to do is say heat, so now here's the first, we want to make this a subroutine of that. And then you have to think, well, which one are we going to ask to do the work? And maybe you could fake it so either could do the work, but I guess we're changing values in the top one, right? So we're going to say, hey, top one tree, we want to add a subtree to you. And top tree, we're going to call your routine called attach left. And what are we going to give you? We're going to give you a pointer that we're going to specify that node over there with P3. And where are you going to put it? We're going to attach it on the left. And right, so there you can see the left. And who are we going to attach? We're going to attach the entire tree. Oops. See that button? If I'm looking up there and push that button, oh, yeah, then life is not good. Build trees. Hello? Why isn't it letting me? Oh, maybe we killed everything. Here we go. Here we go. There we are. That one link didn't work, did it? All right, so what are we doing? Right? So we have to get those links hooked up. Right? And so we're going to write this routine attach left. And we pass it a position, right? This P3 position is P, and T2 is going to be this tree down here. And right, so we get a new variable inside, right? We're inside of tree, this tree, tree 1 has a variable T1, which is now pointing at this entire tree, right? It's not pointing at a node, it's pointing at a tree, right? And so it's not going to return anything. And we're going to say n dot left, right? we got to change this pointer. We want it to point down here, right? So how do we get this? We have n, and we say n dot left, right? And then where's this node? Who's pointing at this node? It's the root. And whose root? It's T2's root, right? So we say T2 dot root, right? T2 is this whole tree. T2 dot root is the value that's here. What value is here? Well, it's this node, right? So now this n dot left is this spot, and T2 dot root is this node. So now this node is, this thing is pointing here, right? Everybody good with that? Right, and now we got to do the other one. We got to change this guy, right? So who we want to point here. So who's pointing at this thing here? N's pointing at this thing. N has the address of this. All right, so there, N has the address of this. And where do we want to put it? Well, T2 dot root dot parent is this box, right? You following this? It's crazy, eh? You can see it gets a little muddly, and that does that link. And now, what's our new size? Right, 9, right? I trust your math, but we got to say our new size, right? Here I just say size. This guy, why can't I just say size and not tree dot size or something, right? It's because I'm actually inside of that tree. So I can just say tree. But then what am I adding on? Well, there's a long chain here. Here's this tree is pointed to by tree 2, right? Which then gets passed into here to T2. And then we say T2 dot size is this value 3, right? Yeah? Sorry, which one are you doing? You really got to trace it out and see what. I really believe that you should have the picture and know what type everything is. All right. So T2 comes from tree 2. So what is it type? It's of type tree, and it's pointing at this tree. And one of the fields in this tree is what are we doing? We're doing root. So it's one of the fields in this tree is the root. So when you say T2 root, you get that box up there. And what type is it? It's type pointer to node. And who is it pointing at? Pointing at that node. So T2 dot root, right, is this node. And when you have a node, one of its fields is parent. So you can do dot parent, and that gives you this box right here. Now, what value is in that box right now? It's probably null because it's a root. But we're going to change it to point here. Did I answer your question? All right. Everybody see, follow, it's good to, you know, at the last class at the beginning, people might have been saying, oh, pointers, and why are you doing green boxes and red boxes? This is silly, right? But you can see it can get pretty muddly. You know what I'm saying? When you're doing all of this, what's going where, it's not easy. It's not easy, right? And then you throw on top of it all this casting, right? And passing things in and out. You pass, it was a tree too, and then it got passed in, and then you cast it, right? It's a little crazy. All right? Right? So now the problem is that you have two trees that share the same nodes. And that doesn't seem nice to me, right? It's probably not what you want. So one option is when we do this operation, we don't just link up the nodes, we actually make a copy of the nodes to put up there. That's one option. And the other option is to destroy T2, right? Or we could disconnect tree 2, right? So here, we're going to go with the option of this routine that we're writing is going to say, I'm now going to destroy your T2 because we don't want nodes appearing in two places. So we say 2t.root is null, right? So if anybody then looks into T2, it doesn't have any no. Oh, and we probably should say size is 0. Do I think of that? Right, so that does that. And so, right, there's my size is 0. What's that black line doing it coming in? Oh, it gets rid of that stuff, right? Size is 0. And, right, so now this is the one tree, and that's the other tree. Yeah?
T2 is null.
They're different, very different things, right? So you would be, there is memory that's storing the value of root and the value of size, right? We have a tree here. And what I'm doing is I'm removing the nodes from that tree. It's still a tree of size 0, right? Now, what you would be doing is you would be dropping the tree, and garbage collection would have to come and clean it up.
Oh, in that case, that wouldn't be connected to this old tree. Is that what you're saying?
If I said, let's look at it. If I said T2 equals null, right? Well, let's compare various things. Tree 2 equals null, right? Tree 2 is pointing at the structure that has a root and has a size, right? And what I'm doing is I'm setting these values to 0. And what you're doing is dropping this link. So this is floating and needs to be garbage collected, right? So, I'm not saying what you're doing would be horrible. I'm just saying it's different.
Just trying to understand. If we do it the way I suggested, it would still work. Like we would still have this connection that we connected these two trees.
Yeah. Yeah. It would be this. See, all these nodes that were here are pointed to by somebody else, right? And so when garbage collection came, it would remove this. That would no longer exist, but the nodes would still be pointing to by somebody else. and that would be fine.
In that case, I think it's better to just delete the tree itself, because otherwise, if you just set null and 0 later can be changed again and still somewhere else can point to same node. But if you
No, I mean, what I'm saying is tree 2 is still this root, it's an empty tree. And then what can you do with tree 2? I mean, those nodes are gone, right? But now I have tree 2. I could call, give me a new root, right? Now it's just an empty tree, which I can do whatever I want with, right? It's like I could it sort of makes sense to me. The outside, what do I want to do to the outside user? It's reasonable to take all the tree's nodes, but it seems a little unkind to shoot the tree, right? Now, another issue, which is worth noting, suppose I do this, right? What's the difference between this and this? Right? So the outside world has a variable tree 2, right? And it has some value, 362, it's an address. And then when we call our routine, it creates a new stack frame. And the new stack frame has a variable P2. And the value gets copied over, 362, right? There's a difference between call by value and call by reference, right? And I could be wrong, but I'm pretty sure Java is called by value. It probably has both. Anybody, but if you don't say, it's called by value, right? So if I inside change this value to null, it has no effect on the outside world. Is what we're saying, right? Yeah. Yeah, exactly. Yeah. People get, back in my day, remember when I was talking about go-tos? Another thing people hated were global variables, right? If it's deep inside, you change a variable somewhere else, and people just don't like that. It's like, who's messing with my variable, right? So, yeah, I would be very surprised if I called a routine and it changed the values of my variables. Everybody good? Yeah. I say everything's a pointer, all right? But they're pointing at different things, right? The outside world has a variable tree2, which then copies in here to T2. And you see what they are is they're pointing at the tree, right? While, what was the other one you named? T2, so then you go T2.root. Now we're at that little root thing, which should be pointing at the root node, right? So tree 2 is of type binary tree, and T2.root is of type node, right? So you should it's really good to keep type checking, right? What type is this? And if it's of type tree, then I can do .root. And if it's of type node, I can do .parent. So that allows me to do T2.root.parent. Right? Does that make sense? Yeah?
The node. Is the node not pointing to the entire tree, or is it pointing to the root of the other tree?
It's just, no, it's, so that's, so binary trees, there's a root that points at the root, and then each node, which at the root node, and then each node points at nodes. So nobody in here is pointing at trees, right? So what are we left with? We're left with tree is pointing at this tree who has a root variable, root field, and that root field is pointing at this node, which 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 is pointing at Vancouver. Right? Did that answer your question? Right? So that's why pictures are really good, right? Hmm?
For example, tree has three levels. So it's got the parent node
Right.
that has two children nodes.
Yeah.
And then its left node has two more children nodes.
Yeah.
You set the root to null.
Yeah.
Why would that cause the entire tree to be erased?
All right. Good question. So we have this tree, and we're saying he's going to just turn this to be 0. All right. Now who's pointing at this node? Is there anybody pointing in this node? No. So Java would say anything not pointed by anybody gets deleted. All right. So then it's gone. Well, now who's pointing at this node? Nobody. And so it snowballs. Right? Does that make sense? Anybody else? Everybody good? All right. Right, so this is, oh, here we have, yeah.
If I were to do the same type of work, keep right down.
Yeah.
So then write function that manually goes through individual levels.
Yes. Yes.
Or you have a
Yes. Yeah. In fact, what I would do, and I think anybody would do, would say there's a recursive structure here. And if I wanted to delete an entire tree, I would call it recursively. I would recursively say, delete my left child. And that would delete my left child and all his children, right? And I would recursively delete my right child. And then I'm only left with my root, which I delete. Yeah?
approach.
Bottom up. Bottom up to me means you start at the leaves and come up. And I don't have access to the leaves. Well, the order they get deleted is from the leaves. So what really happens is I'm at the root. I call my friend who's, right? So this is what would actually happen. Oh, I lost one of my windows. Right, so I call this guy recurses to delete all this stuff. And this guy recurses to delete all this stuff. And this guy says, oh, I'm the empty tree, I'm done. And then we come back up and we delete all this stuff. And then and so this is the first node that actually gets deleted. And then your recursion bops back up. Right?
It depends the location you're at.
Yeah, I mean, we're going back to recursion here, which if we hadn't done it, we haven't done recursion yet. So I think we're beyond what we need to do right here. All right, this is when, suppose you have lots of children, right? So the node, what does the node then look like? Well, this is a node, and instead of having a left child, right child, it points at another structure, which is maybe a set data structure, right? Or an array data structure, a collection. What do I have? I probably have a list of children, right? And so here's my list of children, and each one points at one of the children, right? Does that make sense? Set or list or storing the positions of all your children. And that is the end of those slides, right? How are we doing for time? 5 minutes. Well, 25 minutes. Do I talk too fast? Anybody think I talk too fast? You guys are okay? Okay, good. Any questions about this? I know when we first started with those pointers, people were thinking, oh, this is a little silly. But what do you think in hindsight? Were those early slides, were they okay? Get us warmed up? Because it does get tricky. Doesn't it get tricky? I think it gets tricky. I have sympathy. So whenever I have slides, past the end slide are slides that I made that I deleted. And you can decide if, you don't have to look at them. I just kept them because it's